So we'll start with the review of sampling and estimation, that is reading number 10 of the CFA curriculum. We'll start by understanding an introduction to applied statistics, what the sampling distribution is. Very importantly, understand the central limit theorem, calculate the standard error, calculate confidence intervals, understand the t distribution, and wind up by understanding some biases that can creep in the process of sampling and estimation. So in many real-world applications, it is difficult, if not impossible, to study an entire population. For example, if we were asked to calculate the average age of all CFA and FRM candidates of the world, then the only exact way to do so would be to go to each of these 30,000 possible candidates, ask them their age, sum it all up and divide by 30,000. Now, it would be difficult, and if we only want an average sense, then we won't want to invest so much time and effort in collecting so much data and doing the whole process. So we can make an estimate about this average or about the average age by observing the statistics of a smaller subset called a sample. So I can take some sample and calculate the average age of that sample and use that to calculate an estimate of the average of the population. In a simple random sample, each item has the same probability of getting selected in the sample. So for example, a sample of 50 students of Instructors Mumbai Center, would it be a simple random sample of CFA and FRM candidates? It would not be a random sample because people in India have a higher probability of being in that sample, or people in Mumbai have a higher probability of being in that sample. Each of those 30,000 don't have the same probability of being in the sample. If I choose any 50 random numbers between 1 and 30,000, then that sample would be a random sample, and if I take the ages of those 30 or 50 candidates and take their average, then that will be an estimate from a simple random sample. Now, if I take this sample of 50 students and I calculate the average age of those 50 students, will that average be exactly the same as the average of the population? It is highly unlikely that they will exactly be the same. They may be close, but they will not exactly be the same. So we work with samples because it is too expensive to work with the whole population. Sampling error is defined as the difference between the sample mean and the actual value or the population mean. This error cannot be avoided. If I'm working with samples, some error will come. The objective is just to ensure that the error is within acceptable limits and it doesn't create big problems in whatever economic application I'm doing this analysis for. So whether the average age comes out to be 30 or 32, will the product design differ materially? So if there's a mild error or a small error, it's not a big problem. If the average actually is 30 and my average is coming out to be 60, then the sampling error is quite high. So sampling error will always be there because we are working with samples. It is a difference between the sample mean and the population mean. We can sometimes follow something called a stratified random sampling, wherein the population is first separated into smaller groups, and then from each subgroup a random sample is taken. For example, if I was to calculate the average age of a country with 10 states, and each state has an equal population, then how do we make a simple random sample? In a simple random sample, we will randomly take any 10 people. All 10 of them can come from the same state also. It is possible. In a stratified random sample, if we need a sample of 100 people and there are 10 states, we will first break the process into taking 10 different samples from the 10 states. So we will take 10 samples from each state, and each of those samples will be a simple random sample. So what that ensures is that each state has some representation. So if our objective is to ensure that, then we can do a stratified random sampling. In a simple random, all 100 possibly could have come from one state also, because it's a simple random sample. All items have the same probability of getting selected. Time series data consists of observations taken over time. For example, monthly stock returns of Reliance Industries for the last 20 months. That's also a set of data. It is data collected over time. I can calculate an average. I can calculate a standard deviation that will tell me how the data is dispersed around the mean. Cross-sectional data consists of observations taken at a single point in time. So the returns of all stocks in the Nifty 50 or the S&P 500 for the previous quarter would be an example of cross-sectional data. So all that data has been collected at the same time. And that's also 50 different values that we can try to analyze. Now, a very important concept is that of the sampling distribution. So remember, a sampling distribution is a distribution of all possible sample statistics computed from a set of equal sized random samples drawn from the same population. Let's understand in detail. So let's assume there is a population of CFA and FRM candidates, for instance. There are 30,000 different data points in this population. And I decide to cut samples of size 50 each from the whole population. Sample 1, sample 2, sample 3, sample 4. They are different. They need not be mutually exclusive, but they need to be different. So this will be a different sample, even though there may be some overlap. So how many such different samples can I cut? If there are 30,000 candidates and I have to cut samples of size 50 each, then 30,000 C 50 is the total number of different samples that can be cut. In short, there are many samples that I can cut, or there will be a very high number of samples of size 50 that can be cut from this population. Now, the objective of taking any of these samples was to estimate the average age of CFA and FRM candidates. So each of these samples, which has 50 values, can I sum up the 50 ages and divide by 50? That will give me some indication of the average of the population. Remember, the average of the population is represented by the symbol mu. The average of any sample is represented by the symbol x bar. So if I cut many different samples, then I will have many different sample means also. So the sample statistic in this case is the sample mean, because we are trying to estimate the average age. We could have tried to estimate the standard deviation also. So we could have tried to estimate the sample standard deviation also. But we are trying to estimate the mean of the population using the mean of a sample. Different samples will have different means. As I take samples, I can average them and I can keep calculating the means. Each of these means will have a sampling error. What the sampling distribution is the distribution of these means. So if I take many different samples and I take many different means, then those means themselves is a set of data. And those means themselves can be plotted in a distribution. Now let's assume that my original distribution of CFA and FRM candidates had a shape like this. So most of the students were around 30 years old. There were some very old students taking the exam in the age group of 60, and there were few very young students taking the exam in the age group of 19 or 20. So most of the people concentrated around the age of 28 to 35, and that's where most of the values are. So any distribution is simply values on the x-axis and probabilities or frequencies on the y-axis. So most of the data is concentrated around the mean. Some very old people, some very young people. If I take many different samples and I calculate the means of those samples, then those sample means can themselves be plotted in a distribution that is called the sampling distribution. The question is that if my population had a distribution like this, would the sampling distribution look something like this? That is distribution A, or will it look something like distribution B? Distribution A has a mean of the mean of means, because these means are the constituents, and then the mean of this whole distribution will be the mean of these means. So there's a double bar that I'm putting. Question is that will the sampling distribution, that is a distribution of the sample means, look like distribution A, or will it look like distribution B if this was my population? The difference between distributions A and B is that A is a relatively less dispersed distribution. That is, the values are closer together. Most values are close to the mean and lesser values are further away from the mean as compared to the original distribution. Whereas distribution B is a more dispersed distribution. Values are not all clustered together. Values are further away, or the dispersion is higher. So what's it going to be? A or B? Now, individually, the population may have a 60-year-old also. It may have a 19-year-old also. However, when I start taking the means of 50 together, if 60 is the extremest value, then can 60 ever be a sample mean? Because it will always get clubbed with some 49 other values and the value will be lesser. So if the original distribution was like this, the sampling distribution will be closer. It will have a lesser dispersion because some averaging we are already doing. Individually there may be a 19-year-old, but in a sample of 50, and especially if you're taking simple random samples, then those sample means will be relatively closer to each other. They may not all exactly be the same. Just like the mean of the sample may not be equal to the mean of the population, but they will definitely be closer together. So the sampling distribution, very important, is a distribution of the sample means. If the original population had a mean of mu and a standard deviation of sigma, then the sampling distribution has a mean of mu, or an expected mean is still the same as the mean of the population, but it will have a dispersion or standard deviation equal to sigma by root n, where n is the size of the sample. Remember, n is always equal to the size of sample. If I take samples of size 100, then that averaging process will be even better, because groups of hundreds together will have closer averages than groups of 50. So the dispersion would be even lesser. So the sampling distribution has a lesser distribution or has a lesser dispersion than the population, to the extent of the population standard deviation upon root n. Sampling distribution is a distribution of sample means. Why we need it and what is the big advantage of doing this calculation, we will see in the coming slides. However, fine, for now, I just want you to understand very well what is the definition of the sampling distribution and why it has a lesser dispersion. What we studied is also described in the central limit theorem that says that for simple random samples of size n from a population with a mean mu and a finite variance sigma square or a standard deviation equal to sigma, the sampling distribution of the sample mean x bar approaches a normal probability distribution with mean mu and a variance equal to sigma square by n as the sample size becomes large. Now, the central limit theorem is extremely important and has great implications for practical problems. So it says that the population can be any distribution. The population needn't be a normal distribution. However, if we are taking simple random samples, then the sampling distribution, that is the distribution of the sample means, will always be close to a normal probability distribution. So my original data can have any distribution. It can have such a distribution also. Highest values at 0 and very low values at a value equal to 10. Original population can have any distribution. As long as you're taking simple random samples, please note what will happen. In a random sample, some values of 0 will come, some value from the middle can come, some extreme can also come. If you take simple random samples and plot the distribution of the means of those samples, then the means of the samples will follow a normal distribution. That is, most of the means will be closer to the population mean, and then there will be some dispersion. So the original distribution, if it is normal, very good, then definitely so this will also be a normal distribution. But even if original distribution is not normal and we are taking large enough samples, large here implies sample size should be greater than 30, then the sampling distribution follows a normal probability distribution with the same mean as that of the population, or with the same expected mean as that of the population, and a standard deviation equal to sigma by root n, or variance equal to sigma square by n. Now, the proof of this theorem is beyond the scope of the curriculum. So it's not a maths exam, it's a finance exam. We need to understand the applications of what the mathematicians have developed well. So we will believe the central limit theorem. It's been developed with a lot of research. So that's what we've found, that if you take samples of size greater than 30, then sampling distribution still tends to be normal. The implications it has is that we can apply all properties of the normal distribution that we have studied hitherto into our analysis of the samples and into our estimation of the population parameters. Now, if n is sufficiently large, the sampling distribution will be approximately normal regardless of the shape of the population. The mean mu of the population and the mean of the distribution of all possible sample means are equal. The variance is sigma square by n, that is the population variance divided by the sample size. Just a review of the central limit theorem. The distribution of sample means has an expected value or an expected mean equal to the population mean and a standard deviation equal to sigma by root n. The standard deviation of the sampling distribution is also called the standard error. So the sampling distribution has a mean mu variance sigma square by n. The standard deviation of this distribution, the distribution that comes from the means of different samples, is also called the standard error of the distribution. If the population standard deviation sigma is known, we already studied, the standard error will be sigma by root n, or the standard deviation of the sampling distribution will be sigma by root n. If sigma is not known, that is, if the population standard deviation is not known, then as an approximation, we can estimate the standard error to be equal to s by root n, where s is the sample standard deviation. So preferably we want the population standard deviation. If that is not known, however, then we will use the sample standard deviation as a proxy for the population standard deviation. The mean height for the employees in a firm is 5.8 feet with a population standard deviation of 1.1 feet. Calculate, and very importantly, interpret the standard error of the sample mean for a size of 49. So first, let's do the calculation. The standard error calculation is simple. It is the standard deviation of the population upon square root of n. Standard deviation of the population is 1.1 and n is 49. So it will be 1.1 upon square root of 49. Thank you. That is 1.1 upon 7, which comes out to be 0.157. The second part says interpret the standard error. The interpretation is that if I take simple random samples of size 49 from this population, then the distribution of those sample means, and if I calculate the mean of each of those samples and I plot those means in a distribution, then the distribution of the sample means will approximately be a normal distribution with a mean equal to 5.8, that is the same as the population, and a standard deviation of this distribution, that is also called the standard error, equal to 0.157. Consider a sample of 45 CFA aspirants from India for June 2013 level 1 exam. The mean score of an aspirant in the sample is 72% and the standard deviation is 18%. Calculate and interpret the standard error of the sample mean. So the only problem in this case is that the population standard deviation is not given. If the population standard deviation was given, this would have been exactly the same question as the previous one. So when the population standard deviation is not given, then as a proxy, we use the sample standard deviation to calculate the standard error, that is the sampling standard deviation of the sampling distribution. So the sample standard deviation is given to be 18% upon square root of 45. So square root of 45 is 6.7. Store this in 1. 18 divided by recall 1 come out to be 2.7 approximately. The interpretation is the same. If I cut simple random samples of size 45 and I take the means of each of those samples, then the distribution of the sample means will approximately be a normal distribution with a mean equal to 72% and a standard deviation, also called the standard error, equal to 2.7%. Now, the application of all that we have studied up till now comes in calculating the confidence intervals for my estimates. The reason why we need the normal distribution assumption, the reason why we need the central limit theorem, is basically that we will be able to give very precise estimates and very precise confidence intervals about our data or about our population mean if I have this analysis. So point estimates are single values used to estimate a population parameter. So if I just take one sample and calculate the mean of the sample, then that will be a point estimate for the population mean. Confidence interval is a range of values in which the population parameter is expected to lie with some degree of confidence. So if somebody asks me what is the mean age of CFA and FRM candidates, I can either give him a point estimate, take a sample of 50, calculate, and I say the expected value is 32. Probably a better way to answer that question would be that 95% of the times it is expected to be in the range of 28 to 35. So expected value is 32, but 95% of the times it should be within 28 to 35. That kind of an answer would be a confidence interval about the population parameter. Definitely helps us in finance, definitely gives us a clearer picture, definitely gives us an indication of the worst case, best case, 95% of the times. So the confidence interval is calculated as the point estimate plus minus a reliability factor into the standard error. Please note that this confidence interval will depend on the standard deviation or the standard error. The higher the standard error, the more dispersed the values can be. The lower the standard error or the standard deviation, the closer together the values will be. So if the expected value is 32, then we would need some sense of the standard deviation before we can give a confidence interval. This reliability factor comes or can be easily calculated because the central limit theorem tells us that our sample means move like a normal distribution. So we study the properties of the normal distribution. 68% of the values lie within one standard deviation of the mean, 95% approximately lie within two standard deviations of the mean. So we can get the reliability factor from the normal distribution assumption, as we will do in the coming slides. So point estimate is the value of a sample mean or a sample statistic. Reliability factor depends on the sampling distribution. If it's a normal distribution, it will be different. If it's a logarithmic distribution or a Poisson distribution, it will be different. And it depends on the confidence interval. So if you want to be 95% sure, the range will be smaller. If you want to be 99% sure, then the range will be bigger. So 95% of the times it lies within this range. 99% of the times it lies within 25 to 40. And standard error is the standard deviation of the sampling distribution or the standard error of the point estimate. Applying the central limit theorem, the mean will be the population mean. The standard deviation will be sigma by root n, that is the standard error. And the reliability factor can be estimated from a normal distribution. Alpha is the level of significance. It is equal to 1 minus the confidence level that we want to have in our estimate. So if alpha is 5%, that means the confidence level will be 95%. So we want to tell that 95% of the values or or 95% of the times, the mean will be within what range? We will start with the sample mean, that is the expected value, and then the range will be determined by the standard error. If 5% is the level of significance, that means 95% of the values must be covered by me, or 5% I can leave out. If I have to leave 5% of the values out, from the right tail, how many would I leave out? 2.5%. From the left tail again, 2.5%. So I will have to see the Z table and see the value corresponding to 97.5, which comes out to be 1.96. We'll verify this from the table as well. And we also did this when we studied probability distributions. So 95% of the times, because it is a property of the normal distribution, that values lie within plus minus 1.96 standard deviations from the mean. So Z alpha by 2 implies I'm leaving 2.5%. If 5% is the level of significance, then 2.5% I have to leave this side, and 2.5% I leave on the left hand side. So 95% of the times the values will lie within x minus 1.96 into sigma by root n and x plus 1.96 into sigma by root n. For 95%, this value is 1.96. If it was a 90% confidence, then I leave 5% on the right and 5% on the left. The value would have come out to be 1.645 because I would have seen the cumulative Z table corresponding to 95%. With a 99% confidence, that means the range that I'm giving, I'm 99% sure the value will lie within these values. That means I have to cover 99% of all possibilities. So 0.5 I leave on that side and 0.5 I leave on the left. Please note, I can never be 100% sure because at the end of the day I'm working with a sample. The only way to be 100% sure about the mean is to calculate the entire population's mean. Until that point, whatever we do will be an estimate. I can be 99% sure, I can be 99.5% sure also, but I can never be 100% sure. Tails of a normal distribution extend till infinity. They never meet. So you can never be 100% sure. With 99%, the reliability factor would be 2.58. So 99% of the times the values will lie within plus minus 2.58 standard deviations of the mean. We'll do an example and understand it better. So consider a data set comprising yearly returns for the last 49 years for Reliance Industries. The mean return was found to be 10.8%. Assuming a population standard deviation equal to 2.3%, construct and interpret a 99% confidence interval for the mean return on the stock for 49 years. So construction normally is the easy part. It is the interpretation that you must understand. So for 149-year sample, we find that the mean return was 10.8 from the population of, let's say, 100 years of returns. There were many samples of size 49 that I could cut. In one such sample, the mean of the sample came out to be 10.8%. Question asked is not construct and interpret a confidence interval for the Reliance annual returns. That is not the question. If the question was to construct a confidence interval for the Reliance annual returns, then it would be 10.8 plus minus the standard deviation, that is 2.3 into 2.58. Because in 1 year, dispersion can be a lot. Like we studied, the original population can have a higher distribution or a higher dispersion as compared to the sampling distribution. The question asked is, construct and interpret a 99% confidence interval for the mean return on the stock for 49 years. That is, if I take another sample of 49 years and another sample of 49 years, then what is likely going to be the mean of those samples? The means of samples have a standard deviation that is lesser than the population standard deviation. So the means of the samples have a standard deviation equal to sigma by root n, that will be equal to 2.3 divided by root 49. So individual annual returns can be highly dispersed. So in this case, if I take any other 49-year period and I calculate the mean return in that period, then the expected value of the mean return is 10.8, and 99% of the times the mean return will be in the range of 10.8 plus 2.58, that is a reliability factor, or 2.575 for a normal distribution, multiplied by the standard error, and 10.8 minus 2.58 into 2.3 upon root 49. So let's calculate. 2.3 divided by 7 multiplied by 2.58, 2.3 divided by 7 multiplied by 2.58. We'll store this in the memory register 1. 10.8 we'll store in the memory register 2 minus recall 1, that is 9.95, and 10.8 plus recall 1 is the 99% confidence. So 99% of the times the value will be in the range of 9.95 to 11.65. That is the mean of another sample. If I take the mean of another 49 years of returns, then that mean is expected to be in this range 99% of the times. Once again, if the question didn't ask us for the mean return on 49 years, if the question simply asked us, construct the confidence interval for Reliance annual returns, then in any 1 year, the returns can be highly dispersed, right? It is in the 49 years averaging that the dispersion will come down. So if I was just asked the annual return confidence interval, then I won't do 2.3 divided by root 49. I will just do 2.3. Now this will normally not be the case in this review. Normally in sampling and hypothesis testing, we are trying to calculate the mean of something. So we are worried about the standard error more than the individual standard deviation. So in most cases, we'll do standard deviation divided by root n. But you have to be careful that if it is on the means of data, then it is sigma by root n. Let's just verify. For 99% confidence interval, how much am I leaving on the right hand side? 0.5. So this area, this dark shaded area for a 99% confidence interval is going to be 99.5%. For a 90% confidence interval, this black shaded area, because I'll have to use 5 here and 5 on the left hand side, which is a symmetric distribution, the normal distribution. So the dark shaded area will be 95%. So I can check the value corresponding to 99.5%. So see where 99.5 comes. So we see somewhere around 2.5, 0, 1, 2, 3, 4, 5, 6, 7, and 8. So we say 2.575 is where 99.5% of the values lie. Similarly, if we see where 95% comes, so we see 95% comes somewhere here. That will be 1.6, 0, 1, 2, 3, 4, 5. Somewhere between 1.64 and 1.65. So that's how the reliability factor comes. It comes from the Z table or the normal distribution assumption. The standard values for 90, 95, 97.5 and 99% we have to remember. And as we do in the coming slides, we will memorize each of those values. Now the central limit theorem works for large sample sizes. That is when the sample size is greater than or equal to 30. What when the sample size is less than 30? Or what in the case of small samples? So generally we cannot apply the central limit theorem and we cannot apply the statistics that we just did if the sample is less than 30. In some circumstances, however, even with smaller sample sizes, we can apply our statistics with the help of a t-distribution. So a t-distribution is symmetrical like the normal distribution. It is a bell-shaped curve also like the normal distribution. Unlike the normal distribution that is defined by two parameters, that is the mean and the variance, the t-distribution is defined by a single parameter called the degrees of freedom. The degrees of freedom simply are n minus 1, where n is the size of the sample. So the t-distribution has fatter tails as compared to the normal distribution. So if df was the normal distribution, df1 would be the t-distribution. So t-distribution has fatter tails than a normal distribution or more probabilities in the extremes. We'll study in other financial applications that it has been seen that normal distribution many a times underestimates the probability of extreme events. That is, the tails of a normal distribution are too thin, or the probability of extreme events are very small when measured through a normal distribution. A t-distribution has fatter tails, that is, it has more probabilities of values being in the extreme. As the degrees of freedom becomes large in a t-distribution, as the sample size becomes large, degrees of freedom is just n minus 1. The shape of the t-distribution tends to become closer to a normal distribution. If the sample size is greater than 100, or in a very large sample, the t-distribution will have almost a similar shape as a normal distribution. Now we don't need to remember the specifics and the values of the t-distribution as we have to in the case of a z distribution or a normal distribution. The application of the concepts with the t-distribution is very simple. So, or is very similar. That is, instead of x bar plus minus z alpha by 2 into sigma by root n, if it's a t-distribution that the variable follows, then we will do x bar plus minus t alpha by 2 into sigma by root n. That is, our critical values or our reliability factor will come from the t-distribution. If it comes, the values will be given to you. You do not have to memorize the values for a t-distribution. But remember, if you are working with a large sample and you are sampling from that is your population, is a normal distribution with known variance, then with a large enough sample, you can apply the central limit theorem and use the normal distribution. If sample size is small, if the population itself is normal, then you can again use the normal distribution assumption. So if the population is normal, then you can use the normal distribution in all cases, small and big sample. If it is a normal distribution with unknown variance, however, Then for small samples, it is advised that you use the t-statistic. For larger samples, also it is advised you use the t-statistic to be conservative, but you can use the z-statistic also, or you can use the normal distribution also. If it is a non-normal distribution, then with less than 30, statistics is not available. Again, for a non-normal with unknown variance, less than 30 sample size, you can't do anything. If it is a non-normal distribution with known variance and a large sample, then samples will approximately be a normal distribution. That is what the central limit theorem says, even if the distribution is not normal. And if it is a not normal distribution with unknown variance, that is population standard deviation is not known, then again it is advised you use the t-statistic. However, even z-statistic is allowed or can be used. So for large samples, you can use the normal distribution generally. Some places it is advised to use the t, but even a normal assumption would do. For non-normal with unknown, or for normal distribution with unknown variance and small size, you should use the t-statistic. The exact application of the t-statistic is very similar as the z-statistic. The values you don't need to remember. The next concept tells us about the properties of a good estimator. So, if I've been asked to estimate the average age of all CFA and FRM candidates, that is, I'm estimating the mean of the population, then what should my estimator be? Should it be the mean of the sample, or should it be the median of the sample, or should it be the mode of the sample? So I'm estimating the population mean. The best parameter or the best statistic to calculate from the sample to estimate the population mean will be the sample mean. The reason is because the sample mean satisfies three properties of a good estimator. First, a good estimator is unbiased. That is, the expected value is equal to the population parameter. So expected value of the sample mean is equal to the population mean. But if it's a symmetric distribution, then mean, median, mode are all the same. So expected value of the median is also the same as the population mean. The good estimator is also efficient. That is, amongst all unbiased estimators, the sampling distribution for this parameter or this statistic has the lowest variance as compared to all unbiased estimators. And finally, a good estimator is consistent. That is, the accuracy of the estimator increases as the sample size increases. So these three properties are satisfied by the sample mean. So to estimate the population mean, we must use the sample mean. Remember, a good estimator is unbiased, efficient, and consistent. Expected value is the same as population, lowest variance amongst all unbiased estimators, and is consistent such that the accuracy increases as the sample size becomes large. Finally, let's understand some biases that can come in the process of sampling and statistics. First is generally we are advised to take a large sample because large sample reduces the sampling error. The value will be closer to the population mean. However, if we take a very large sample, then it's possible that I have incorrectly pooled the data or I have incorrectly taken observations from a different population. So I wanted a sample for CFA and FRM candidates. In my enthusiasm for collecting a large sample, I have even included people who are thinking about taking CFA, who are not yet candidates, who haven't yet enrolled, who are thinking about enrolling or who are in 2 minds. So strictly speaking, that should not be done because we need the sample of CFA and FRM candidates. So in 2 large samples, this is a mistake that can sometimes come in. cost of taking a large sample should be weighed against the increase in precision. So if there is not much improvement, then no point wasting your time on effort in collecting a very large sample. Data mining bias is another problem. So data mining bias is when you dissect the data or you beat the data so much so that you find a relationship that you are looking for. Now, what this pattern says that results are a chance pattern after repeatedly searching the data for some identifiable pattern. So in data mining bias, the statistical significance of our statement tends to be overestimated. For example, I claim that I am a good fund manager. However, if you see the 1 year performance, 3 year performance, last 5 year performance, my funds seem to have underperformed most other funds, peers, as well as the benchmark. But I still claim I am a good fund manager. Now, definitely, if I beat the data, there will be some 3-month period in which my funds did the best amongst all funds. Or there'll be some 1 month or 4-month period in which I did the best. So if I cut the data to show only those time periods, then that will not be the right thing to do. So data mining bias is that when you're looking for some identifiable pattern, and hence you're just trying to see phases where that pattern is visible. So the statistical significance of this is nothing, or it means nothing. It doesn't show any sustainability or consistency. So these bias is something that you should be careful about. Sample selection bias is very common, wherein some data is being systematically excluded from the sample, making the sample non-random. Because central limit theorem, please remember, works for simple random samples. So if the samples are not simple random or they are biased, then the theorem does not work or cannot be applied. Survivorship is a very common example of the sample selection bias, wherein we see that often in calculating the performance of funds, it is only the surviving funds that are included. And when we calculate the data like that, the performance of hedge funds looks very good. The performance of a lot of other funds also looks very good. We see the average hedge fund performance over the last 10 years is so much. What that average excludes is the funds that have shut down operation. So a fund that has survived for the last 10 years probably would be amongst the better performing funds. And obviously, if we take the average of only this group, then the data will be overestimated because there were so many funds that started and shut down because their performance was so bad. Actually, when I'm calculating the performance of the hedge fund universe, I should look at the performance of all funds and then make a conclusion about the performance of hedge funds. If I only take the surviving funds, then there is sample selection bias, there is survivorship bias, which can bias my results upwards. Look ahead bias is when you are using sample data that was not available on the test date. For example, a study based on year-end price to earnings ratio, where normally stock price is always available. Stock price is available every day. I can look at the market and I know the stock price. So on 31st December, that is the year end, I get the stock price, but I have to compute the price to earnings ratio for that year. Now, on 31st December, would I have the earnings data as well? Companies take some time before compiling, auditing their results, and then disclosing the earnings to the public. However, if I'm calculating the P by E ratio for the last 4 years, then the 31st December price would be available. It would be available for each of these years. I can look back and see what the stock price was at that time. Will the earnings now be available? Because we are here, this is past data. In the past, the prices also be available and the earnings will also be available. However, earnings weren't reported at this time. Earnings were reported later. So this stock price did not know this earnings exactly. When the stock price was P, however, did the people at this time know these earnings? You know it because you are working in hindsight. So if I do the PE ratio analysis in this way, that is, I use the year-end stock price and the year-end earnings data, then I'm ignoring the fact that people at this stock price did not know what the earnings would be. So concluding anything out of this type of analysis may be incorrect. What you should do is you should take a 3-month later price, because 3-month later price would have had the price as well as the earnings data available to everybody. So look ahead bias is when you're using sample data that was not available on the test date. Finally, if the time period is too long, then I will get a lot of data. My sample will be big, but I may be incorrectly pooling the data, because if we were to discuss about India's GDP growth, then for all practical purposes, before 1991, India was a different country. After 1991, when liberalization happened, deregulation happened, the economic environment in which the country was operating and the growth was happening was completely different. So if I pool last 50 years of data, that will make my data non-stationary. What this means, we will study at level 2, but it is not the right thing to do, because 50 years is not comparable. It is again you're comparing or you're pooling in two different populations. If I keep the time period too short, that is only last 2 years of GDP growth, then that again may not be a representative sample, that may have a data mining bias, or that will produce results that are not statistically significant. With too long a time period, underlying fundamental relations could have changed if data is pooled over a very long time period. So these are some biases that you should be careful about. Too large a sample can have problems: data mining bias, sample selection bias, survivorship bias, look ahead bias, and time period bias. So that was about the review on sampling and estimation, an important input that will go into many calculations and that will go into the review of hypothesis testing that we will study next. So thanks a lot, and see you in the next